This introductory chapter explains reinforcement learning from human feedback, RLHF, as a technique to align AI systems, especially large language models, LLMs, with human preferences. It details the typical three-step RLHF process: supervised fine-tuning, SFT, training a reward model based on human preference data, and optimizing the LLM using reinforcement learning guided by this reward model. The chapter positions RLHF within the broader context of post-training methods, distinguishing it from simple instruction tuning by emphasizing its role in teaching stylistic nuances and improving generalization. It traces the historical development and adoption of RLHF, including recent shifts like direct preference optimization, DPO, while acknowledging its complexities, costs, and challenges like over-optimization. The chapter concludes by outlining the book's scope, structure, and the anticipated future role of RLHF in advancing AI alignment and capabilities. 1. Introduction. Reinforcement learning from human feedback, RLHF, is a technique used to incorporate human information into AI systems. RLHF emerged primarily as a method to solve hard-to-specify problems. Its early applications were often in control problems and other traditional domains for reinforcement learning, RL. RLHF became most known through the release of ChatGPT and the subsequent rapid development of large language models, LLMs, and other foundation models. The basic pipeline for RLHF involves 3 steps. First, a language model that can follow user questions must be trained, see Chapter 9. Second, human preference data must be collected for the training of a reward model of human preferences, see Chapter 7. Finally, the language model can be optimized with an RL optimizer of choice by sampling generations and rating them with respect to the reward model, see Chapter 3 and 11. This book details key decisions and basic implementation examples for each step in this process. RLHF has been applied to many domains successfully, with complexity increasing as the techniques have matured. Early breakthrough experiments with RLHF were applied to deep reinforcement learning, SOS, deep reinforcement learning from human preferences, advances in neural information processing systems, vol. 30, 2017. Summarization SOS, learning to summarize with human feedback, advances in neural information processing systems, vol. 33, pp. 3830-21, 2020. Following instructions SOS, training language models to follow instructions with human feedback, advances in neural information processing systems, vol. 35, pp. 27732-7744, 2022. Pausing web information for question answering SOS. Webbed, browser-assisted question answering with human feedback. Archive preprint AZIV 2112, 09332, 2021. And alignment, SOS, training a helpful and harmless assistant with reinforcement learning from human feedback. Archive preprint AZIV 2204, 05862, 2022. A summary of the early RLHF recipes is shown below in Fig. 1. Figure 1 depicts the early 3-stage RLHF process. It starts with a base model which is trained using human instructions, around 10K examples, to become an SFT, supervised fine-tuning model. Separately, human preferences, around 100K examples, are used to train a reward model. Finally, the SFT model is optimized using PPO, proximal policy optimization, guided by the reward model and reusing preference prompts, resulting in the final aligned model. In modern language model training, RLHF is one component of post-training. Post-training is a more complete set of techniques and best practices to make language models more useful for downstream tasks. SOS, T/ULU3, Pushing Frontiers in Open Language Model Post-Training. Archive preprint AZIV 2411, 15124, 2024. Post-training can be summarized as using 3 optimization methods. 1. Instruction/supervised fine-tuning, IFT/SFT, where we teach formatting and for base of instruction following abilities. This is largely about learning features in language. 2. Preference fine-tuning, pre-FT, where we align to human preferences and get smaller bump in capabilities at the same time. This is largely about style of language and subtle human preferences that are hard to quantify. 3. Reinforcement fine-tuning, RFT, the newest type of post-training that boosts performance on verifiable domains. This book focuses on the second area, preference fine-tuning, which has more complexity than instruction tuning and is far more established than reinforcement fine-tuning. That being said, RLHF colloquially is what led to modern post-training. Soon after the release of ChatGPT, RLHF encompassed all of post-training. The foundations of RLHF involve far more than preferences alone, and this book provides introductions to all the related topics. 1.1. What does RLHF do? The biggest question around RLHF, yet one that is still hard to answer, is what does RLHF training offer models? The core role of this book, beyond teaching the techniques for doing RLHF, is to distill intuition as to why RLHF is crucial to modern AI models. In recent years, language models have shifted from academic experiments studied in the purview of benchmarks to general-purpose technology. RLHF is at the core of this transition. To start, let us consider how a language model at the end of autoregressive pretraining answers a query. A strong model, Llama 3.1405b, will continue from the President of the United States in 2006 was. George W. Bush, the governor of Florida in 2006 was Jeb Bush, and John McCain was an Arizona senator in 2006, who later lost to Obama. September 1, U.S. President Bush signs an executive order to provide more options for faith-based organizations when delivering social services that are paid for with federal funds. January 1, the current deadline set by United States Congress in the Unlawful Internet Gambling Enforcement Act, ACA-UIGA. Search amendments to the 1961 International Convention for the Protection of New Varieties of Plants require plant breeders' rights, include farmers' privilege. 2009 was a common year starting on Thursday of the Gregorian calendar, the 2009th year of the Common Era, C, and Anno Domini ad designations, the 9th year of the third millennium, the 9th year of the 21st century, and the 10th and last year of the 2000s decade. What is clear is that this model is completing the sentence and adding other common internet metadata. The most compelling view of how RLHF works is to think of how style applies to interactions you have with language models. The style, or format, of information presented is crucial to how it is learned. This has always been the case for examples such as coursework, but is normally applied in the background and not considered directly. Continuing the above example, a model trained with RLHF and other post-training tools would answer the question very differently. Asking Tulu 3405b the same question, the President of the United States in 2006 was, says concisely. George W. Bush was the President of the United States in 2006. He served 2 terms in office, from January 20, 2001 to January 20, 2009. Modern research has established RLHF as a general method to integrate subtle stylistic and related behavioral features into the models. Compared to other techniques for post-training, such as instruction fine-tuning, RLHF generalizes far better across domains, SOS, understanding the effects of RLHF on LLM generalization and diversity. Archive preprint OZIV 2310, 06452, 2023. SOS, SFT memorizes, RL generalizes, a comparative study of foundation model post-training. Archive preprint OZIV 2501, 17161, 2025. Helping create effective general-purpose models. Intuitively, this can be seen in how the optimization techniques are applied. Instruction fine-tuning is training the model to predict the next certain token when the text preceding is close to examples it has seen. It is optimizing the model to more regularly output specific features in text. This is a per-token update. RLHF, on the other hand, tunes the responses on the response level rather than looking at the next token specifically. Additionally, it is telling the model what a better response looks like, rather than a specific response it should learn. RLHF also shows a model which type of response it should avoid, i.e. negative feedback. The training to achieve this is often called a contrastive loss function and is referenced throughout this book. While this flexibility is a major advantage of RLHF, it comes with implementation challenges. Largely, these center on how to control the optimization. As we will cover in this book, implementing RLHF often requires training a reward model, of which best practices are not strongly established and depend on the area of application. With this, the optimization itself is prone to over-optimization because our reward signal is at best a proxy objective requiring regularization. With these limitations, effective RLHF requires a strong starting point. So RLHF cannot be a solution to every problem alone and needs to be approached in a broader lens of post-training. Due to this complexity, implementing RLHF is far more costly than simple instruction fine-tuning and can come with unexpected challenges such as length bias, SOS. A long way to go, investigating length correlations in RLHF. Archive preprint RZIV 2310, 03716, 2023. SOS, Disentangling Length from Quality in Direct Preference Optimization. Archive preprint RZIV 2403, 19159, 2024. For projects where performance matters, RLHF is established as being crucial to achieving a strong fine-tuned model, but it is more expensive in compute, data costs, and time. 1.2. An intuition for post-training. Here's a simple analogy for how so many gains can be made on mostly the same base model. The intuition I've been using to understand the potential of post-training is called the elicitation interpretation of post-training, where all we are doing is extracting and amplifying valuable behaviors in the base model. Consider Formula 1, F1. Most of the teams show up to the beginning of the year with a new chassis and engine. Then, they spend all year on aerodynamics and systems changes. Of course, it is a minor oversimplification and can dramatically improve the performance of the car. The best F1 teams improve way more during a season than chassis to chassis. The same is true for post-training. The best post-training teams extract a ton of performance in a very short time frame. The set of techniques is everything after the end of most of pre-training. It includes mid-training, like annealing/high-quality end of pre-training web data, instruction tuning, RLVR preference tuning, etc. A good example is our change from the first version of OLMOE Instruct to the second, the post-training evaluation average from 35 to 48 without touching the majority of pre-training SOS. OLMOE Meet iOS. https://alani. org/blog/olmoapp, 2025. Then, when you look at models such as GPT-4.5, you can see this as a way more dynamic and exciting base for OpenAI to build onto. We also know that bigger base models can absorb far more diverse changes than their smaller counterparts. This is to say that scaling also allows post-training to move faster. Of course, to do this, you need the infrastructure to train the models. This is why all the biggest companies are still building gigantic clusters. This theory folds in with the reality that the majority of gains users are seeing are from post-training, because it implies that there is more latent potential in a model pre-training on the internet than we can teach the model simply such as by passing certain narrow samples in repeatedly during early types of post-training, i.e. only instruction tuning. Another name for this theory is the superficial alignment hypothesis, coined in the paper Lima. Less is more for alignment sauce. Lima. Less is more for alignment. Advances in Neural Information Processing Systems, Vol. 36 pp. 550655021, 2023. This paper is getting some important intuitions right, but for the wrong reasons in the big picture. The authors state, a model's knowledge and capabilities are learnt almost entirely during pre-training, while alignment teaches it which subdistribution of formats should be used when interacting with users. If this hypothesis is correct, and alignment is largely about learning style, then a corollary of the superficial alignment hypothesis is that one could sufficiently tune a pre-trained language model with a rather small set of examples. Kirstein et al. 2021. All of the successes of deep learning should have taught you a deeply held belief that scaling data is important to performance. Here, the major difference is that the authors are discussing alignment and style, the focus of academic post-training at the time. With a few thousand samples for instruction fine-tuning, you can change a model substantially and improve a narrow set of evaluations, such as Alpaca Eval, MT Bench, chatbot arena, and the likes. These do not always translate to more challenging capabilities, which is why Meta wouldn't train its Llama chat models on just this dataset. Academic results have lessons, but need to be interpreted carefully if you are trying to understand the big picture of the technological arc. What this paper is showing is that you can change models substantially with a few samples. We knew this, and it is important to the short-term adaptation of new models, but their argument for performance leaves the casual readers with the wrong lessons. If we change the data, the impact could be far higher on the model's performance and behavior, but it is far from superficial. Base language models today, with no post-training, can be trained on some mathematics problems with reinforcement learning, learn to output a full chain of thought reasoning, and then score higher on a full suite of reasoning evaluations like Big Bench Hard, Zebra Logic, AIME, etc. The superficial alignment hypothesis is wrong for the same reason that people who think RLHF and post-training are just for vibes are still wrong. This was a field-wide lesson we had to overcome in 2023, one many AI observers are still rooted in. Post-training has far outgrown that, and we are coming to see that the style of models operates on top of behavior such as the now popular long chain of thought. 1.3 How we got here. Why does this book make sense now? How much still will change? Post-training, the craft of eliciting powerful behaviors from a raw pre-trained language model, has gone through many seasons and moods since the release of ChatGPT that sparked the renewed interest in RLHF. In the era of Alpaca, SOS, Stanford Alpaca, an instruction-following LLMA model, GitHub repository. https://github.com/tatsulab/Stanford Alpaca, GitHub, 2023. Vicuna SOS, Vicuna, an open-source chatbot impressing GPT-4 with 90% asterisk ChatGPT quality. 2023. SOS, Koala, a dialogue model for academic research. Blog post 2023, and Dolly SOS, Hello Dolly, democratizing the magic of ChatGPT with open models. Accessed, June 30, 2023. A limited number of human data points with extended synthetic data in the style of self-instruct were used to nominally fine-tune the original LLMA to get similar behavior to ChatGPT. The benchmark for these early models was fully vibes and human evaluation, as we were all so captivated by the fact that these small models can have such impressive behaviors across domains. It was justified excitement. Open post-training was moving faster, releasing more models and making more noise than its closed counterparts. Companies were scrambling, e.g. DeepMind merging with Google or being started, and taking time to follow it up. There are phases of open recipes surging and then lagging behind. The era following Alpaca et al. The first lag in open recipes was one defined by skepticism and doubt on reinforcement learning from human feedback, RLHF, the technique OpenAI highlighted as crucial to the success of the first ChatGPT. Many companies doubted that they needed to do RLHF. A common phrase, instruction tuning is enough for alignment, was so popular then that it still holds heavy weight today despite heavy obvious pressures against it. This doubt of RLHF lasted, especially in the open where groups cannot afford data budgets on the order of $100 K to 1M. The companies that embraced it early ended up winning out. Anthropic published extensive research on RLHF through 2022 and is now argued to have the best post-training SOS. A general language assistant as a laboratory for alignment. Archive preprint AZIV 2112, 00861, 2021. SOS, training a helpful and harmless assistant with reinforcement learning from human feedback. Archive preprint AZIV 2204, 05862, 2022. SOS, constitutional I, harmlessness from I feedback. Archive preprint AZIV 2212, 08073, 2022. The delta between open groups, struggling to reproduce, or even knowing basic closed techniques, is a common theme. The first shift in open alignment methods and post-training was the story of direct preference optimization, DPO, SOS, direct preference optimization. Your language model is secretly a reward model. Advances in Neural Information Processing Systems, Vol. 36, 2024. The DPO paper, posted in May of 2023, didn't have any clearly impactful models trained, with it going through the fall of 2023. This changed with the releases of a few breakthrough DPO models, all contingent on finding a better, lower learning rate. Zephyr Beta Sauce, Zephyr, Direct Distillation of LM Alignment, in First Conference on Language Modeling 2024. Tulu 2 Sauce, Camels in a Changing Climate, Enhancing IAM Adaptation with Tulu 2, Archive Preprint RZIV 2311, 10702, 2023. And many other models showed that the DPO era of post-training had begun. Chris Manning literally thanked me for saving DPO. This is how fine the margins are on evolutions of best practices, with leading labs being locked down. Open post-training was cruising again. Preference tuning was something you needed to do to meet the table stakes of releasing a good model since late 2023. The DPO era continued through 2024 in the form of never-ending variance on the algorithm, but we were very far into another slump in open recipes. Open post-training recipes had saturated the extent of knowledge and resources available. A year after Zephyr and Tulu 2, the same breakout dataset, Ultra Feedback is arguably still state-of-the-art for preference tuning in open recipes, SOS. Ultra Feedback, Boosting Language Models with High-Quality Feedback, 2023. At the same time, the Llama 3.1 SOS, the Llama 3 herd of models, Archive Preprint RZIV 2407, 21783, 2024. And Nematron 4 340B SOS, Nematron 4 340B Technical Report, Archive Preprint RZIV 2406, 11704, 2024. Reports gave us substantive hints that large-scale post-training is much more complex and impactful. The closed labs are doing full post-training, a large multi-stage process of instruction tuning, RLHF, prompt design, etc., where academic papers are just scratching the surface. Tulu 3 represented a comprehensive, open effort to build the foundation of future academic post-training research, SOS, T/Ulu 3, Pushing Frontiers in Open Language Model Post-Training. Archive Preprint RZIV 2411, 15124, 2024. Today, post-training is a complex process involving the aforementioned training objectives applied in various orders in order to target specific capabilities. This book is designed to give a platform to understand all of these techniques, and in coming years, the best practices for how to interleave them will emerge. The primary areas of innovation in post-training are now in reinforcement fine-tuning, reasoning training, and related ideas. This newer methods build extensively on the infrastructure and ideas of RLHF, but are evolving far faster. This book is written to capture the first stable literature for RLHF after its initial period of rapid change. 1.4 Scope of this book. This book hopes to touch on each of the core steps of doing canonical RLHF implementations. It will not cover all the history of the components nor recent research methods, just techniques, problems, and trade-offs that have been proven to occur again and again. 1.4.1 Chapter Summaries. This book has the following chapters. 1.4.1.1 Introductions, reference material useful throughout the book. 1. Introduction, overview of RLHF and what this book provides. 2. Seminal, recent, works, key models and papers in the history of RLHF techniques. 3. Definitions, mathematical definitions for RL, language modeling, and other ML techniques leveraged in this book. 1.4.1.2 Problem setup, and context for the big picture problem RLHF is trying to solve. 4. RLHF training overview, how the training objective for RLHF is designed and basics of understanding it. 5. What are preferences? Why human preference data is needed to fuel and understand RLHF. 6. Preference data, how preference data is collected for RLHF. 1.4.1.3 Optimization tools, the suite of techniques used to optimize language models to align them to human preferences. This is a serial presentation of the techniques one can use to solve the problems proposed in the previous chapters. 7. Reward modeling, training reward models from preference data that act as an optimization target for RL training or for use in data filtering. 8. Regularization. Tools to constrain these optimization tools to effective regions of the parameter space. 9. Instruction tuning. Adapting language models to the question-answer format. 10. Rejection sampling. A basic technique for using a reward model with instruction tuning to align models. 11. Policy gradients. The core RL techniques used to optimize reward models and other signals throughout RLHF. 12. Direct alignment algorithms. Algorithms that optimize the RLHF objective direction from pairwise preference data rather than learning a reward model first. 1.4.1.4. Advanced newer RLHF techniques and discussions that are not clearly established, but are important to current generations of models. 13. Constitutional AI and AI feedback. How AI feedback data and specific models designed to simulate human preference ratings work. 14. Reasoning and reinforcement fine-tuning. The role of new RL training methods for inference time scaling with respect to post-training and RLHF. 15. Synthetic data. The shift away from human to synthetic data and how distilling from other models is used. 16. Evaluation. The ever-evolving role of evaluation and prompting in language models. 1.4.1.5 Open questions, fundamental problems, and discussions for the long-term evolution of how RLHF is used. 17. Over-optimization. Qualitative observations of why RLHF goes wrong and why over-optimization is inevitable with a soft optimization target in reward models. 18. Style and information. How RLHF is often underestimated in its role in improving the user experience of models due to the crucial role that style plays in information sharing. 19. Product UX character. How RLHF is shifting in its applicability has major AI laboratories use it to subtly match their models to their products. 1.4.2 Target audience. This book is intended for audiences with entry-level experience with language modeling, reinforcement learning, and general machine learning. It will not have exhaustive documentation for all the techniques, but just those crucial to understanding RLHF. 1.4.3 How to use this book. This book was largely created because there were no canonical references for important topics in the RLHF workflow. The contributions of this book are supposed to give you the minimum knowledge needed to try a toy implementation or dive into the literature. This is not a comprehensive textbook, but rather a quick book for reminders and getting started. Additionally, given the web-first nature of this book, it is expected that there are minor typos and somewhat random progressions. Please contribute by fixing bugs or suggesting important content on GitHub. 1.4.4 About the author. Dr. Nathan Lambert is a RLHF researcher contributing to the open science of language model fine-tuning. He has released many models trained with RLHF, their subsequent datasets, and training codebases in his time at the Allen Institute for AI I2 and Hugging Face. Examples include ZephyrBeta, Tulu2, OLMO, TRL, OpenInstruct, and many more. He has written extensively on RLHF, including many blog posts and academic papers. 1.5 Future of RLHF. With the investment in language modeling, many variations on the traditional RLHF methods emerged. RLHF colloquially has become synonymous with multiple overlapping approaches. RLHF is a subset of preference fine-tuning, pre-FT techniques, including direct alignment algorithms. See Chapter 12. RLHF is the tool most associated with rapid progress in post-training of language models, which encompasses all training after the large-scale autoregressive training on primarily web data. This textbook is a broad overview of RLHF and its directly neighboring methods, such as instruction tuning and other implementation details needed to set up a model for RLHF training. As more successes of fine-tuning language models with RL emerge, such as OpenAI's all-reasoning models, RLHF will be seen as the bridge that enabled further investment of RL methods for fine-tuning large base models. At the same time, while the spotlight of focus may be more intense on the RL portion of RLHF in the near future as a way to maximize performance on valuable tasks. The core of RLHF is that it is a lens for studying one of the grand problems facing modern forms of AI. How do we map the complexities of human values and objectives into systems we use on a regular basis? This book hopes to be the foundation of decades of research and lessons on these problems.